Hi, my name is Atanasov. I'm cloud native engineer at Intel Network and Edge Group. Today, a wide range of applications from AI, HPC, and visualization domain rely on GPU offload to accelerate computations. With the rise of WebAssembly, users now can deploy in portable and secure way their technical compute applications also in cloud native environments. Recent introduction of new web APIs and WASI interfaces such as WASI-NN and WebGPU allow access to GPU offload also in WASM space. The demo will show the basic usage and characteristics of those API for several WASM compute examples from AI, deep learning in practice, and illustrate those steps needed to integrate them in cloud-native environments. Applications such as GPU offload are supported on a wide range of APIs in the ecosystem for native deployment. We can structure those APIs in three main fields: visualization APIs, scientific APIs, and emerging APIs for AI. Visualization APIs are typically OpenGL, Vulkan, DirectX 12, and for scientific compute, we see OpenCL, SQL, CUDA as examples for such applications. WebAssembly provides a new path to achieve portability and high-level security without compromising performance for cloud native. Some of the top efforts to bring GPU offload in those segments are done through specific WASI APIs for AI, such as WASI-NN, or through more generic approaches such as WebGPU and their WASI counterparts. Let's zoom in on AI-specific approaches such as WASI-NN. This method identified that machine learning and deep learning models are deployed on a wide variety of hardware devices. As a lot of the optimizations required to run optimally on those hardware are hard to include in WASM executables, this method makes use of WASI interfaces to pass the model in the form of open standards such as ONNX to an external AI framework which then implements the hardware optimizations. This allows achieving near to native performance and does not compromise on security. The API for using WASI-NN is quite simple, targeting basic loading operations for the computational graph, also setting input and output for the graph and triggering the computations. Now I will give the microphone to my colleague Aaron, who has prepared an interesting demo for AI inference with WASI-NN.
Hi, I'm Aaron. I'm going to be doing a quick run through of WASI-NN, just using an example courtesy of the WASI-NN examples repo. So here we just want to use a basic road segmentation model to break up segments of a road from an image. An example use case for something like this would be in autonomous driving. So here we just have a basic Rust file where we use the WASI-NN crate. We load in a precompiled road segmentation model into this graph structure here. Next, we read in the input image and convert it to a useful tensor. And afterwards, we feed that into the precompiled model and run the compute function here to get some output. After that, we just output that into a tensor that we can use for later, say for analysis, or if we want to feed it into another model. So I'm just going to compile this Rust file here. I've already precompiled it. And next, I'm going to feed that into WASM Edge just to run it. So we got a .wasm binary out of compiling that Rust there, and we're just going to feed it into WASM Edge. We're also going to pass in the precompiled road segmentation model, and we're using an OpenVINO backend. So we're going to run that there. That's going to pass the input image into the model, and it should give us an output tensor here, which we've gotten. And we're just going to use a Jupyter notebook to process that data. So we are just going to first visualize the original image, and that should pop up here. And next, we're just going to parse the output tensor to view it visually. You can clearly see some of the road markings here are segmented. Next, we're going to perform some RGB operations to create a mask that we can then put over the original image. And finally, we should get the original image, the output tensor that we got from the model, and a masked image, which is something like what you might see in the camera of an autonomous vehicle. Thanks for watching.
Let's move on. We have another more interesting things to cover. And next API is a generic rendering API called WebGPU, which was published by the 3W consortium and made available to WASM ecosystem through a Rust-based WebAssembly library called WebGPU. This API can run on top of different backends, such as DirectX 12, Metal, or Vulkan, providing portability across different GPU architectures. It comes with major rendering and compute APIs supporting different shader models and delivers significant performance and security improvements versus WebGL. WebGPU compute shaders first bring pure compute capability to web. With them, we can do arbitrary reads and writes to storage buffers or texture locations, which is perfect for AI kernel implementations. Access shared workgroup memory, which corresponds to a piece on chip GPU memory with much lower latency and higher performance than global memory on modern GPUs. WebGPU compute shaders utilize it to provide a highly efficient way to share data among all threads in one workgroup. All of those make WebGPU compute shaders powerful and flexible. We talked about a lot about graphics and the WebGPU standard, but it can be also utilized for AI applications, and there are a lot of integrations with major inference frameworks, such as TensorFlow GS and ONNX Renta. WebGPU also comes with natural improved interoperability with visual processing pipelines. Later, we will showcase how those two can be combined. Following cartoons are showing some of the benefits of WebGPU in terms of performance. I'm going to demonstrate today how we can use WebGPU in WASM through a WASI component model. We will define a simple compute example in WebGPU through a compute pass. The compute pass uses a compute pipeline, which is bound to several storage buffers, and the compute shader through a pipeline. On the left, we see a classical WebGPU native application. On the right window, we see a WebGPU application written for WASI component model. A careful looking at the code shows us that the two APIs are nearly identical. The application which we have today consists of a simple shader code with two inputs, a result, which is an input and output, and another buffer we call input. The result buffer is used to calculate the sum of the original result input and the input buffer. Later in the application, we create the two buffers and the staging buffer, which we will use to read the result. We create a pipeline, a compute pipeline, and we send a bind group inside the compute pass, which associates buffers with shader. To dispatch work via the compute pass, we use the length of the array so that we know how many workers we will have on the x-axis. After dispatching that work, at the end, we want to copy the resulting addition, the resulting numbers in the staging buffer. And the staging buffer, after submitting this work to the device, will be mapped to user space. Let's build this application. First, we need to compile a WASM executable. This can be done with cargo build and the WASM32 unknown target. After building this executable, we need to build a component out of it, a WASI component, and this can be done with the WASM tools provided together with WASM. The component we can observe through WASM tools, and we see that it includes WebGPU interface and exports a start function, which can be used to trigger the component. Let's start a computation. For that, we will use an example runtime, which implements WebGPU interface. And to execute our new component, we have to point to it through the name of the component. We called, in this example, the component compute. After several seconds, we get a result, which is the sum of the vectors, of the two vectors consisting of 5 elements. And the result was calculated on a Vulkan backend provided by the driver of the system. And we see a correct calculation of the sum of the two vectors. Thank you very much for your attention. I hope you enjoyed our demo today. If you are looking for more information about it and the references listed here, thank you very much.